at the top of the board here, we've got a limit that we know how to evaluate. We've got f of x, which is this rational function, x squared minus 4 over x minus 2, and we're taking the limit as x approaches 2. Now, we can't plug in 2 because, of course, that makes the top and the bottom both go to 0, but we can factor the top. It's a difference of 2 squares, so we factor it as x plus 2, x minus 2, and we can cancel the x minus 2. And so we can say this is the limit as x goes to 2 of x plus 2, a different function because this function would be defined at 2, but a function that has the same limit because it's the same as f of x everywhere except at 2. And in evaluating this limit, we can just plug in 2, so we get 2 plus 2, our limit is 4. So we know that. But here's the task we're given. We're being asked to find a positive number delta. Delta being bigger than 0 just specifies that it has to be a positive number, such that if this inequality is true. Now I want to remind you that the absolute value of x minus 2 just means the distance between x and 2. So that would be the horizontal distance on the x-axis between our x value and the number 2. And we want that distance to be between 0 and delta. So that's saying that x isn't 2 because it's some positive distance away from 2, but it's close to 2, where delta is our standard of closeness, or our tolerance for how close we want that x value to be. And we're supposed to find a delta so that if this inequality is satisfied, so if x is close to 2 using delta as a standard of closeness, then this inequality will be satisfied. This absolute value is the vertical distance between f of x, the y value on my function, and 4, the number that we're claiming is the limit. And I want that distance to be less than 0.01. So that's essentially the tolerance that I have for the outputs of this function, or for the y values. That's the standard of closeness we're using for the y values. So that's essentially my epsilon. So it's as if we made this claim that this limit is 4, and somebody came along and they said, I don't believe you. You are claiming that you can make your y values get close to 4. I bet you can't get that close, where this close is 0.01. They give us a tolerance, and they're saying, I bet you can't make your function value be within that tolerance. Okay. So we're going to do that. We're going to show that we can by finding a delta. Now, the formal definition of a limit says that we would be able to do this no matter what positive number we were given here. Right now, we're just going to work through it for this particular positive value. So this isn't going to be a formal proof because we're only demonstrating that we can meet this challenge, this one challenge where the epsilon value is 0.01. To do a formal proof, we have to be able to prove that we can meet all challenges for any positive number epsilon that we could be given. And we'll do that in the next video. But here I want to just sort of take a look at remembering what it means to actually find this delta that works. Notice we're given the epsilon, so we know what that is, and our task is to find a delta that makes this if-then statement true. Okay, so I'm going to draw myself a picture. Now, f of x was x squared minus 4 over x minus 2. I can simplify that. That's just x plus 2 with the restriction that x isn't 2. So when we canceled that x minus 2, I said that this x plus 2, that's a different function, but it's the same as f everywhere except at 2. So if I record this restriction that 2 is not in the domain, then this is just a simpler way of writing f. And what's nice about that is that makes it easy to graph, because then it's just going to be a line of slope 1 with a y-intercept at 0, 2, and it's going to have a hole in it at 2, 4. Okay, excellent. Let's make it so that that looks like that's actually where I put my second tick mark. So that's at 2, and the y value's at 4. Okay, excellent. So now I'm going to just draw a picture of this challenge that we've got to meet. Now if this is 4 and I want to be within 0.01 of that, we could go up to 4.01 or down to 3.99. Now, obviously right here, I am not drawing this to scale. The reason I'm not drawing it to scale is that if I did, you wouldn't be able to see it, or I'd have to zoom in so much that you'd no longer be able to tell that this was the line that we were working with. Okay, so I'm purposely just ignoring the scale, but sort of getting a symbolic picture. I want my y values to be within this strip of values that I can actually even color code. I want to be in the purple range. Okay. So I can see that I can follow my graph a little ways to the left. And I'm just going to mark this off as x1. And I can follow it a little ways to the right. And I'm going to mark this off as x2. Okay. And this is 2 right here in the middle. It does look like these numbers are the same distance away from 2. And they actually should be, because this line doesn't change steepness. So it's going to cover this vertical distance of 0.01 over the same horizontal distance on either side. So I should find that x1 and x2 are the same distance away from 2. All right. Now, if I wanted to find x1, I would just say I know that x1 plus 2, because that's what I would get if I plugged it into the function. X1 is clearly not 2, so I can use that formula. That's going to be where my function value is equal to 3.99. So x1 would simply be 1.99. Okay. And then x2, well, that's the function value where x2 plus 2 would equal 4.01. So x2 is simply 2.01. And it does work out that, yes, this distance is the same on both sides. In fact, it turns out to be exactly the same as the value that epsilon was. It's 0.01. But now I can say that's my delta. Okay. So if you're given a specific value of epsilon and asked to find a delta, I do expect you to show some work to justify your answer, but there's some work to justify our answer. That's as much as you would need to show. In a formal proof, we're going to go through a similar process to this to find a delta that we think is going to work. But that's going to sort of be our informal work, and then we're going to write up a formal argument to demonstrate that the delta that we found works. For a specific value of epsilon, our goal was just to find it, not to prove that it actually worked. And so we've succeeded here. Our delta in this case would be 0.01. We can use the same standard of closeness for our x values and our y values.